Good morning, everyone. I'd like to thank the organizers of this conference for inviting me and thank you for attending this talk. I'm Somayeh Sojoudi from UC Berkeley, and this talk is about efficient computational methods with provable guarantees for data-driven problems. Let me start off by briefly motivating the importance of computation in societal problems. We are living in a time where almost all physical systems are getting smarter by incorporating new technologies. For example, legacy power grids are being transformed into smart grids to increase efficiency, reliability, resiliency, and sustainability. And this transformation is based on using solar panels, wind turbines, smart meters, and new power electronic devices. As another example, we are working on the design and implementation of intelligent transportation systems to enable the dream of driverless cars and automated highways. In a broader context, we are moving towards the smart cities that include all sorts of new technologies. However, the operation of these systems is data-driven. More precisely, these systems have a large number of sensors to collect data, which are then passed to mathematical algorithms for processing to gain knowledge about the underlying system. And the knowledge is then passed to the decision-making units to find the best actions for the operation of the system. The operation of smart cities relies heavily on computational tools, and we need to have computational tools that are reliable and efficient so that they can be used for safety-critical systems such as transportation and energy systems. The word efficiency is the key, which is about scalability and quality of solution. Scalability is the ability to solve problems with tens of thousands of variables and millions of constraints under a tight deadline. For instance, one of the most important operational problems in power systems, named optimal power flow, is a large-scale problem that must be solved in less than 5 minutes. Quality of solution means we need guarantees that the obtained solution is not far from the true solution. Aside from scalability and quality of solution, we should ensure that we have enough data. Otherwise, getting a good solution won't be possible. To formalize the notion of scalability, we should look at the time or memory complexity of any algorithm versus the number of parameters. The complexity curve could be linear, quadratic, cubic, or higher orders. And the difference between these complexity figures is whether the problem can be solved in a second, minute, day, or year. To understand the notion of quality of solution, consider a nonlinear optimization problem. Solving it numerically, we might end up getting the best point possible, named global minimum, or a point that is close to it, named near global minimum, or a point that is only locally the best point, named local minimum, or an arbitrary point that is only feasible, or an infeasible point. So there is a wide range defining the quality of a solution. To understand the role of data in this process, note that the amount of data required for extracting useful knowledge depends on the type of the system, such as being dense or sparse or structured. In this talk, we study these 3 important components. In particular, we study learning problems that are formulated as optimization problems. And we know that if the problem is convex, we could use a descent algorithm to find a global solution. But for non-convex problems, we might get stuck at a local minimum that is far away from the globally optimal solutions. So let me start with some learning problems that have convex formulations. For this part, sparsity of the underlying system plays a key role in the design of a scalable algorithm. So the goal is to learn large-scale sparse systems from data efficiently. And the motivation comes from knowing that most large-scale real-world systems have sparse representations. For example, the structures of power grids, genomics, and the stock market can be captured by sparse graphs. And by sparse, we mean these interconnected networks have much fewer connections or edges than nodes. This sparse structure makes it easy to interpret and study such networks. An important question is, how can we learn the model of a system from data? This model can be non-physical, like statistical, or physical, like some real dynamics. To learn a statistical model, we focus on graphical models where the question is how to design efficient algorithms to learn the statistical interactions between the parameters of a system. This problem has a wide range of applications, but in part is motivated by neuroscience. Human brain has more than 100 billion neurons, which can be studied through the notion of brain functional connectivity. This connectivity graph is a very large, sparse graph showing how one region of the brain statistically affects other regions. The counterpart of learning statistical models is learning physical models. We want to know how to learn interconnected dynamical systems, how to design data-driven control policies for such systems, and finally, study how much data is needed to ensure that the data-driven controller performs satisfactorily on the original systems. This work is in part motivated by the area of reinforcement learning, where an agent aims to interact with the environment, learn it, and take appropriate actions. For both problems, sparsity is the key. For statistical learning, we designed low-complexity algorithms for learning sparse graphs. We tested these algorithms on several real-world systems and found models with over 200,000 parameters in less than 2 hours on a standard laptop. In comparison, the best-known algorithms for this problem were not able to find any graph for much smaller problems, even though we allowed them to run for several days. For dynamical learning, we showed that the amount of data required to learn a physical system suffices to be logarithmic for sparse systems. This bound on sample complexity is a lot sharper than the existing results in the literature. Let me give you more details on these results. I'd like to start with the design of efficient algorithms for learning sparse graphical models. The goal of statistical models is to uncover properties of a system from data. This is similar to the system identification problem in control theory, where the goal is to learn mathematical models of dynamical systems from data. But here, we learn statistical models as opposed to physical models. Probabilistic graphical models are statistical models that capture the relationships between the parameters of a system using graphs. They are used in a variety of applications such as medical diagnosis, social networks, image segmentation, speech recognition, power systems, and biological networks. In neuroscience, graphical models are widely used to estimate and explore functional connectivity between different brain regions. Data corresponds to brain signals, which are collected using different imaging technologies, such as EEG, functional MRI, and ECOG. This picture shows different brain imaging techniques compared by spatial and temporal resolution. We can divide these techniques into non-invasive, semi-invasive, and invasive. In the non-invasive technique, the sensors are placed on the scalp to measure the electrical potentials produced by the brain using EEG or the magnetic field using MEG scanners. Another commonly used non-invasive imaging technology is functional MRI, which measures brain activity by detecting changes associated with blood flow. In semi-invasive imaging, the electrodes are placed on the exposed surface of the brain. These arrays of electrodes are referred to as ECOG. Finally, in the invasive case, the microelectrodes are placed directly into the cortex, measuring the activity of a single neuron. So there are different ways to measure brain activities, and each technique measures data with certain spatial and temporal resolutions. Some techniques can measure brain activities at the level of single neurons, which we have more than 100 billions of those, and some at the level of brain regions like sensory motor, visual, and the auditory cortical regions. Each of these regions or neurons will serve as a node in the graphical model. We know that neurons do not work in isolation. They need constant interactions with other brain components to process information. So the edges of graphical models correspond to the effect of each region or neuron on another one. Graphical models are powerful tools in understanding both normal and abnormal brain functions. They help neurologists and neurosurgeons in diagnosis and treatment of various neurological disorders. Now let's formally define graphical models and see how we can learn such models from data. An unreacted graphical model is a graph where each node represents a parameter of a stochastic system, and each edge shows the conditional dependence between two parameters of the system. The picture in the right shows an unreacted graphical model with 4 nodes. If the underlying system is Gaussian, then this graph corresponds to the sparsity of the inverse covariance matrix. That means that the edge of the graph corresponds to non-zero off-diagonal entries of the matrix. The literature on this topic is quite extensive. The main question in this area is how to estimate this graph from data. Given some data, we form the sample covariance matrix. If we have a lot of data, we can treat the sample covariance matrix as the true covariance matrix, take its inverse, and then map its sparsity pattern to a graph. But for many problems, we don't have such amount of data. In that case, we usually use an estimator and map the sparsity of its matrix solution to a graph. The most common estimator used for learning Gaussian graphical models is Graphical Lasso. To explain Graphical Lasso, we start with a system with n parameters, take the measurements, and form a sample covariance matrix. This will be fed into Graphical Lasso with the matrix variable S, and this variable must be positive definite, and it aims to estimate the true inverse covariance. This is a one-norm term in the objective that aims to sparsify the matrix S to help with finding a sparse graphical model. Graphical Lasso belongs to a class of convex optimization known as conic optimization. And for a system with n parameters, it needs to solve for a matrix with n squared elements. This means that if, for example, we want to learn a sparse graph with 1,000 nodes, we should solve for 1 million variables. If we have prior knowledge about some edges of the graph, we should add it to the optimization, and the new problem is called restricted graphical lasso. To simplify the presentation, we only focus on graphical lasso for Gaussian systems, but our results are for arbitrary restricted graphical lasso and applied to exponential family of probability distributions. The best known algorithms for graphical lasso are called G-lasso and Quick. And the computational complexity of these two methods is at least n to the 4 log of 1 over epsilon, where epsilon is the precision error. However, the complexity of reading data is n squared. So there is a huge gap between n squared and n to the 4. But we want to know if there is any way to solve large-scale problems in quadratic time instead of quartic time. We will see in this talk that this is possible for sparse graphs, and this figure shows that by reducing the complexity from n to the 4 to n squared, we can solve very large-scale problems that the algorithms with quartic complexity cannot handle. Here is a summary of our results. Under mild conditions, we showed that Graphical Lasso has a closed-form solution for acyclic graphs, and therefore we don't need to use numerical algorithms. We then extended the results to chordal graphs. For arbitrary non-chordal graphs, there is no precise closed-form solution, but we derived a closed-form formula to find an approximate solution of Graphical Lasso. Since these formulas are based on basic linear algebra, we showed that graphs with over 400,000 nodes could be found in less than 2 minutes. If you want to solve Graphical Lasso precisely, we showed that this could be done in linear time for sparse graphs. Our approach is based on advanced notions in conic optimization, graph theory, linear algebra, and numerical algorithms. I will discuss some of these results next. To study Graphical Lasso, we introduced 3 notions: sign-consistent matrices, inverse-consistent matrices, and beta function. Since the first 2 definitions are a bit involved, let me skip them and just focus on the beta function. The beta function takes a graph G and a scalar alpha and returns a scalar number beta. This number is the maximum of the norm of all matrices N over all matrices M and N, such that the support of M is the graph G, the norm of M is upper bounded by alpha, the diagonal of M is 1, M is positive semi-definite, and the pair M and N is inverse consistent. Using the previous notions, we showed that sparsity of the solution of Graphical Lasso can be found using some thresholding operator if 3 conditions are satisfied. The first one is about a matrix being positive definite. The second condition is about the same matrix being sign consistent, and the third one involves the beta function. To simplify these conditions, we further studied the beta function and proved that for acyclic graphs, beta is quadratic, and for arbitrary graphs, beta is upper bounded by a quadratic function. Using this result and the theorem in the previous slide, we were able to show that Graphical Lasso has a closed-form solution for acyclic graphs, where the formula is the simple equation shown here. In summary, we have a single formula that serves as a solution to a conic optimization problem, and therefore we don't need to use numerical algorithms. We generalized the results to arbitrary graphs and developed a closed-form formula as an approximate solution of Graphical Lasso. We showed that the approximation error, denoted by epsilon, follows a sophisticated equation. By analyzing this equation, it turns out that the approximation error decreases exponentially fast with respect to the length of the cycles of the graph. We tested our closed-form formula on many systems and observed that our method is more than 1,000 times faster than GLasso and 50 times faster than Quick. Also, our approximation error was always less than 0.01%. This graph shows that there is a big range of problems where none of the existing methods could work except for the closed-form technique. In fact, using the closed-form formula, we can solve instances of Graphical Lasso with over 3.2 billion matrix entries in less than half an hour. As I said before, we found that Graphical Lasso has a closed-form solution for acyclic graphs. But note that acyclic graphs are special cases of chordal graphs. As a reminder, a chordal graph is a graph that has no induced cycle of length more than 3. For example, the graph on the left is non-chordal since it contains a cycle of size 4, but the graph on the right is chordal. We proved that the beta function has a nice upper bound for chordal graphs that depends on the tree width of the graph. Tree width has a somewhat complicated definition in graph theory, but informally speaking, tree width measures how close a graph is to being a tree and is a measure of the sparsity of a graph. And since real-world systems like power systems have a bounded tree width, we can replace the tree width in this formula with a constant to obtain a nice expression for this function. By further developing this result, we were able to show that Graphical Lasso has a closed-form recursive formula for its solution if the unknown graph is chordal. We tested our results on the dataset collected by the University of Florida. This dataset includes the graphical networks of many real-world systems in chemical processes, material science, circuits, etc. The picture in the left shows the visualization of some of these systems, and the enlarged graph corresponds to a financial system. To solve Graphical Lasso, we first approximated each of these graphs with a chordal graph. This table shows the performance of our recursive formula versus GLasso and Quick as the two best-known algorithms for this problem. We were able to find graphs with over 30,000 nodes in less than 2 minutes, while the two other algorithms did not converge even in several days. In summary, the method that is based on closed-form solution efficiently solves for chordal graphs without error and for arbitrary sparse graphs with some error. A question arises as, can we solve Graphical Lasso for non-chordal graphs precisely? To answer this question, we use chordal embedding that embeds an arbitrary graph into a chordal graph by adding new edges, and also use techniques in sparse linear algebra, duality, and numerical algorithms. We developed a new algorithm for finding sparse graphs whose time complexity is linear after reading data and quadratic including reading data. In summary, the complexity of solving Graphical Lasso for graphs with bounded tree width is n log 1 over epsilon. We revisited the dataset for University of Florida to solve for those graphs precisely with the accuracy of 10 to the minus 9. Our algorithm found graphs with over 200,000 nodes in less than 2 hours, but the existing methods stopped working for problems of much smaller size. So far, we studied the statistical models. Now, let's very briefly discuss learning dynamics. One important question in this area is how to learn physical systems and how much data is required. To answer this question, we consider canonical model in control theory that is linear dynamical systems expressed as x of t plus 1 is equal to a x of t plus b u of t plus w of t. Here, x is the state, u is the input, and w is the disturbance. We are interested in finding a and b. This is a system identification problem, and there are many methods in the control society on doing this. But our goal is somewhat different from system ID, and we would like to know how much data we need in order to learn a and b with a small error. To study this problem, we consider the following setup. First, we run the system d times, and each for capital T amount of time. Then we record the input and state trajectories for each experiment. After that, we feed the collected data into an estimator. The question is how many times we need to run the system so that we can learn a and b with a small error. So we want to find a good bound on the number d. Note that the amount of data is d times capital T, and since capital T is fixed, we should only study d. Using a least squares estimator, a paper written by Dean et al. Showed that the number of experiments for learning suffices to be linear in the dimension of the system. However, we cannot use this result for real-world systems like power systems with millions of states. To break down the complexity, we leverage the fact that many large-scale systems are interconnected with a sparse structure. This implies that the A and B matrices are block matrices with many blocks equal to 0. In this case, we propose the following lasso-type estimator, which estimates the A and B matrices by minimizing the 2 norm squared of some error dynamics plus a block regularizer. Under mild conditions, we showed that this estimator finds a high-quality estimation of the dynamics of the system if the number of trials is at least logarithmic, where the sparsity level of the system shows up as a constant in this complexity band. To summarize, the required amount of data doesn't need to be linear, and being logarithmic is enough. This means that, for example, instead of doing 1 million experiments to learn the sparse system, we only need 1,000 experiments. So far, we discussed statistical learning and dynamical learning problems that are convex. For the last part of this talk, I will discuss how to deal with non-convex learning problems. There are two important questions here. The first question is, when is a learning problem easy or hard? And this could be about learning a matrix or training a neural network. The second question is inspired by the current practice in the machine learning community, which is, can local search algorithms solve learning problems? I will partially answer these questions in this talk by discussing the new notion of global functions that we recently introduced as a major generalization of convex functions. Later on, Lee et al. Showed that almost every over-parameterized deep neural network is a weakly global function, and that partly answers why training neural networks using local search has been successful. There are many learning problems that are converted to non-convex optimization. And also, some key learning problems like training neural networks and matrix sensing with outliers are not only non-convex but also non-smooth. And a local minimum that is not global for these problems could correspond to a wrong model. But how can we deal with the issue of non-convexity? We can use existing global optimization techniques like convex hierarchies to go around this issue. But these methods are too expensive and not scalable. For this reason, data science and industry mostly rely on computationally cheap local search numerical algorithms. An example of a non-convex learning problem with a huge societal impact is power system state estimation. The goal here is to extract reliable information from data corresponding to power systems. More precisely, there is a large-scale nationwide grid with many sensors that collect data. Data here corresponds to a subset of active and reactive powers at nodes, voltage magnitudes at nodes, and flows over lines. And the information here is the state of the system, which is the set of complex nodal voltages. Power system state estimation is solved every 5 to 15 minutes for monitoring and control of the grid. Based on a report written to the President of the US and Prime Minister of Canada, the Northeast blackout, incurring billions of dollars in 2003, was due to failure of power system state estimation. Now let's formulate the problem. In this equation, BI is the measurement, little x is the unknown state, and AI is the known model. In the perfect scenario that there is no error, BI is quadratic in little x. By defining a new variable, capital X, playing the role of little x transpose, we get a linear measurement equation with rank 1 unknown. This problem is known as matrix sensing in machine learning, where the goal is to find a low-rank matrix, capital X, from linear measurements. Note that a subset of measurements could be grossly wrong. For example, we could have sensor malfunctioning or cyber attack. But how can we extract reliable information from unreliable data? These problems can be formulated as non-convex optimization. But how can we deal with the issue of having bad local solutions because of non-convexity? A local minimum that is not a global minimum is called a spurious solution. Many recent machine learning papers are on spurious solutions for neural networks and matrix sensing. but they mostly rely on ad hoc techniques to drive sufficient conditions for non-existence of spurious solutions. To study this problem systematically, we define a new notion of global functions. We call a function global if it doesn't have a spurious solution in the entire space and is continuous. These are examples of highly non-convex global functions. Let's contrast the class of global functions with four well-known classes of functions. Those are convex functions, quasi-convex, star-convex, and decreasing path. Note that global functions include all these four classes of functions. Among these well-known classes, convex and quasi-convex benefit from the property that they are differentiable almost everywhere. Also, for all these four classes, there is a strictly decreasing path from every point to a global minimum. But both of these nice properties break down for global functions, and there exist non-trivial examples that prove this. This is an example of a global function with no strictly decreasing path from point A to point B. This is a complicated function involving a sinusoidal term that induces oscillation on the top. This is also a global function that is nowhere differentiable. We see that the global functions violate the first principles of well-behaved functions, and this means that we need new machineries to analyze these functions. We studied some important properties of global functions, such as pointwise convergence and composition of functions. I used some of these properties to solve an important problem in machine learning, and that's tensor decomposition. Assume that we have a tensor of order d in terms of a vector y, which is unknown. Our goal is to find y based on incomplete information and noisy measurements. Each measurement is denoted as bi and is a product of some elements of y plus small noise, for example Gaussian, and some measurements could be subject to large corruption. Here, we use an L1 norm estimator instead of L2 norm, since it's known that the L1 norm is a robust estimator that rejects outliers. This estimator minimizes the sum of absolute value of some monomials minus bi. But it's not clear if L1 norm estimator has spurious solutions and how to find a global minimum. We showed that the L1 norm estimator, which is a non-smooth, non-convex optimization, is a global function in the noiseless, complete information case. We then extended this result to incomplete information with outliers in the matrix case and showed that positive, robust principal component analysis, or PCA, has no spurious solution under some technical assumptions. Robust PCA is about learning a low-rank matrix from the measurements of some or all of its entries, while some measurements could be completely wrong. To explain robust PCA, consider this matrix. In this example, unknown entries are shown in black, and measured entries are shown in white. Each measured entry could be correct, shown here with letter G, or corrupted, shown with letter B. But we assume that the type is unknown. To analyze PCA, we map the locations of G entries into a bipartite graph. We do the same thing for B entries. We consider the following regularized L1 estimator with a quadratic function and a term of degree 4. The optimization variables here are little x and z that are used in the decomposition of the true solution M. Note that P omega is an operator that shows what elements of M are measured. The unregularized formulation of this problem is commonly known as the Boer-Monteiro technique. There are different smooth variants of this regularized estimator in the literature. For instance, G et al. Have shown that a smooth counterpart of this regularized estimator has benign landscape, meaning that every local minimum is global and every saddle point has a direction with a strictly negative curvature. But how about the non-smooth version, which is robust to large noise and outliers? In the deterministic case, we showed that the non-smooth regularized function is a global function, and the global minimum is the true solution if graph G is connected and the following inequality is satisfied. This inequality involves condition number of the vectors x and z which are used in the decomposition of matrix M, and some properties of graphs G and B. To simplify the deterministic conditions, we came up with probabilistic conditions that say if at least n log n elements are measured at random and up to a constant number of them are wrong, still we can recover the correct solution. To test these results, we performed the following experiment. We considered an n by n rank 1 matrix, measured all entries of the matrix, and corrupted a constant fraction of them with arbitrary large noise. We then used our L1 norm estimator, which is robust to outliers, and the commonly used 2 norm estimator, which is also non-convex but smooth, to recover the matrix. Both non-convex estimators are solved using stochastic gradient descent. These two figures show the performance of the two estimators. In each figure, the horizontal axis shows different values of n, and the vertical axis shows the percentage of wrong measurements. For each scenario, we generated 100 random matrices and calculated how many of them can be solved successfully to find probabilities of success. Here, darker shades correspond to higher probabilities of success. In summary, L1 norm estimator learns the correct matrix from measurements with up to 35% wrong data, but the 2 norm estimator fails even when only 5% of the data is wrong. One important application of matrix sensing is in computer vision. Tracking objects through video is a huge issue in computer vision. It's used in various video analysis cases, such as robotic navigation, autonomous driving, human-computer interaction, and medical visualization. In all these scenarios, we are dealing with corrupted or noisy data, and when it comes to safety-critical applications, such as autonomous driving, we need reliability and high performance. This motivates us to design algorithms with guarantees on global optimality and robustness. The setting we consider here is unsupervised moving object detection, where moving objects are segmented without prior knowledge of these objects. Consider df frames, each with a resolution dm by dn. We first vectorize each frame and then put all vectors together to form a matrix. We call that matrix M. Note that M is a rank 1 matrix in the case the frames have the same background but possibly different illuminations. A moving object acts as a sparse noise. So the video matrix M is modeled as a rank 1 background plus a sparse foreground. In the equation shown here, UV transpose corresponds to the rank 1 background, and S corresponds to the sparse foreground. Recall this non-convex robust estimator that recovers the true global solution under certain conditions. The first condition is about connectivity of a graph, and the second one is concerned with identifiability of the problem. For the moving object segmentation problem, we want to know when the video satisfies these conditions. That tells us if the solution we obtained is a true global solution. In a follow-up work, we came up with conditions for both the connectivity and identifiability requirements. First, we showed that if a video has a connected background, then each frame contains at least one background pixel. and each pixel is a background pixel in at least one frame. The top figure shows that the frame labeled as 5 has no background pixel, and therefore the graph G is disconnected. In the bottom figure, the pixel labeled as 2 is always foreground, and that makes the graph G disconnected. This confirms that both pixel and frame connectivity are necessary for the graph G to be connected. So far, we provided necessary conditions for connectivity. We also came up with sufficient conditions as follows. Suppose that each pixel of a video is a background pixel in at least one frame. If any single pixel is a background pixel in all frames, then the video has a connected background. Let's illustrate this with an example. The figure on the left shows that each pixel is a background pixel. And in the central figure, we can see that pixel 2 is always a background pixel. These are the two sufficient conditions that we need for connectivity, and we can see in the right figure that the graph G is connected. Note that this condition is relaxed because most videos have corner pixels that are not obscured. The last result is about necessary and sufficient conditions for the identifiability requirement. Assume that the moving object has pm by pn pixels. A video satisfies the identifiability requirement if and only if the two inequalities shown here are satisfied. In these inequalities, C0 is a constant number, which is equal to 49, and PF corresponds to the maximum number of frames in which any single pixel appears as foreground. Intuitively, smaller objects and longer videos relax these conditions. This means that videos with small moving objects and many frames are easier to achieve globally optimal video segmentation. In summary, these results provide deterministic guarantees that the non-convex estimator used to decompose a video has benign landscape, and that the resulting decomposition is unique and globally optimal. Let me conclude this section by some examples. Here we want to detect the moving objects in these two videos. I should mention that the first video is a benchmark example in the literature, but the second video is recorded by my group on the campus of UC Berkeley. In each video, we first vectorize each frame and then put all vectors together to form a matrix. The first video was converted to a matrix of size 19,000 by 164. The second video is almost the same size. We applied our robust estimator to these matrices to decompose them as a rank 1 background plus sparse foreground. In both of these videos, we used a stochastic gradient descent, and as we can see here, we were able to correctly find a global minimum. I'd like to mention that the results of the estimation shown on the right side are without any post-processing and cleaning. To summarize, we discussed a number of learning problems that are formulated as optimization. Some had convex formulations and some non-convex. For convex learning problems, we discussed both statistical and dynamical learning. By leveraging the fact that many real-world systems are sparse, we came up with efficient algorithms and techniques to learn large-scale sparse systems. In particular, for learning sparse statistical models, we focused on graphical models and derived a closed-form solution for chordal graphs. Using this technique, we can solve problems with millions of variables in a few minutes on a simple laptop. For arbitrary non-chordal graphs, we designed a linear time numerical algorithm based on a number of techniques, including chordal embedding, duality, and conjugate gradient. This algorithm can handle problems with 100,000 variables and solve them in a couple of hours. For learning dynamical models, we discussed that sparsity plays a big role in sample complexity. In fact, the amount of data suffices to be logarithmic to find high-quality estimates of the system's model. This logarithmic bound on the amount of data is much sharper than the linear bound that exists in the literature. We also discussed non-convex learning problems that could be smooth or non-smooth. The issue with non-convexity is that we might get stuck at a non-global local minimum. As I mentioned before, convexification techniques are expensive and not scalable. On the other hand, computationally cheap local search methods have no global optimality guarantees. To address these issues, we came up with a new notion of global functions. This notion can ensure that local search can find a global solution. Based on this notion, we studied two important problems in machine learning, namely tensor decomposition and matrix sensing, and showed that under some technical conditions, they belong to the class of global functions and have no spurious solutions. Finally, we demonstrated the efficacy of our techniques on the moving object segmentation problem. Dialing back to the beginning of the talk, we are moving towards smart cities where various networks in each city are being upgraded. The upgrade is happening on both hardware and software systems. We've had a lot of advances on hardware design, such as wind turbines and solar panels for energy systems, and driverless cars for intelligent transportation. However, we need to have accompanying software to support the hardware and enable a safe operation. This needs advances in computational and data-driven methods for complex systems. The development of these methods is related to several topics in many areas, such as optimization, control theory, algorithms, machine learning, artificial intelligence, graph theory, and statistics, among others. As a whole, it's crucial to improve the mathematical science behind data science and artificial intelligence to make them useful for safety-critical societal systems. Before I end the talk, I would like to acknowledge my research group and my colleagues who were involved in different parts of this research. I would also like to thank the funding agencies listed here for their support. Thank you for your attention, and I'd be happy to take your questions.